Hey Science Nines, it's Manchak here with your video lesson for Concept D2 in our Electrical Principles and Technologies unit for Science 9. At this point, you should have worked your way through Concept D1, which had you looking at a number of introductory electrical principles, including static and current electricity, the definitions of amps and volts. We talked about resistance, we talked about electrical safety, all sorts of stuff like that, cells and batteries as well. What you should have done to this point is gone through that lesson, gone through your worksheet, done your practice and summative quizzes, and now you're ready to move on to this. So today we're going to be covering concept D2, which is going to have us looking at controlling current, measuring electricity, and electrical circuits. And we're going to play around with these concepts in here out of the curriculum. So we're going to play around with conductors and insulators a little bit. We'll talk about switches and electrical flow and how they're related to each other. We'll get into talking about voltages and amperages in circuits and how we measure them. We'll talk about Ohm's law, which links resistance, voltage, and current in simple circuits. And then we'll actually get into talking about circuits themselves, how they work, and we'll play around with what we call parallel and series circuits, and then ultimately look at things like microcircuits and circuits in our houses. So it's a loaded thing that we're going to get through. Just to give you a heads up, this will be in the Google Classroom right above where you clicked on this video to watch this. Your textbook pages for this are 296 to 317. I have a whole bunch of videos on here for you. You don't have to go through all of them, especially these sort of first four here. They're just more for interest's sake than anything. But I think it'd be good to have a look at least these three videos and maybe the introduction to simple circuits at the bottom there. Once you've looked over some of your resources here, you've got some questions out of your textbook you can do, and then I'm going to have you guys do an activity on building some circuits using an application I found online that should work on all devices, I hope, including Chromebooks and iPads and touchscreen phones, those kinds of things as well. And there'll be a worksheet associated with a practice quiz as usual, and then you guys will move on to your summative quiz. So in order to save time, why don't we jump back in? So we have now moved into concept D2, which is, we said, covering section 2 in this unit, which is technologies and can be used to transfer and control electrical energy. And so we're going to jump through these that we just went through. I've just left this up here just to show you that if you wanted to do a quick introduction at this point and look at a couple of videos, these ones sort of show you what we can do when we control electrical current, when we can control the flow of electrons moving through a circuit. And so it would be, if you'd like to have a look at these and check them out. One's about neon lights and one's about smart power generation. So it's something for you guys to look at if you'd like to. Controlling the flow of electric current. Electric current flows through complete circuits. Remember, if a circuit is broken for whatever reason, you've got a switch in it, or maybe a wire is broken in that circuit, electricity is not going to flow through it. But electrical current will flow through it if the circuit is complete. The amount of current that can flow through a circuit is limited by the conductive properties of the components in the circuit. In other words, the amperage, or the speed of the charged particles, is dependent on how well the object or objects conduct electricity in that circuit. This means that it's not the electricity that does not flow through materials such as rubber or wood, but that the flow is slowed so much that the material remains neutral. So in other words, rubber or wood that are not good conductors basically slow the flow of electrons so much that everything remains neutral and things aren't really moving at any rate that's going to generate a current at that point. But things like metals, particularly things like copper, which we use in our wires, do an excellent job of conducting current, and meaning that lots of current could actually flow through them if we wanted it to. So this leads me into talking about conductors and insulators. Okay, And these are important terms to remember when we're trying to control the current that is flowing through an object. Okay? An insulator is something in which the electrons cannot move easily through. So looking at this diagram down here, electrons are the little negatives and the protons are the positives, and so they are bound, these electrons are bound tightly to the protons, the positives, meaning that it's hard for them to move their way at all through that. Okay. Now a conductor, on the other hand, is a substance where the electrons can move easily because they're not tightly bound to the nucleus of their atoms. So if you look at, here's our protons and here's our electrons, they're a fair distance away from the nucleus of the atoms. So what that means is they're going to be good conductors. These electrons are more or less free to move within this substance. So a conductor with no voltage applied, the electrons are not as tightly bound to the nuclei, and so they drift away from the nuclei but do not flow. But if we apply a voltage, I want you guys to think of it as it's kind of like pressure. So if we apply some pressure to those electrons by applying a voltage, what's going to end up happening is the electrons are going to flow toward the positive terminal of the voltage source. So if your voltage source is a battery, it's going to flow towards the positive end of the battery, and they'll flow away from the negative end of the battery. So if this is positive and this is negative, they're going to flow away from the negative and towards the positive in our circuit of conductor, whatever that conductor is. Hope that kind of makes sense for you, okay? So that leads us into talking about a superconductor then. Superconductors are materials that have no resistance, or such a tiny amount we can barely measure it, to electron flow. And many materials are superconductive when they become, or when they're experiencing very, very low temperatures. And so what I would encourage you to do right now is hit pause and take a moment to watch this video on quantum levitation, and it'll give you an idea of what a superconductor actually is. So hit pause right now, have a look at that. So now that you've had a look at that video, I want you to sort of think about, why would we want to have a superconductor? A superconductor means there's no resistance to electron flow. So those electrons aren't slowed down at all. So for example, if I'm trying to maximize the amount of electricity that moves through something, the most conductive materials are the best for me. If I'm a power company, if I could afford to do this, I might use superconductors to get my electrons from one spot to another spot, because I'm not losing any energy along the way due to the resistance that normal wires would encounter. Now, is that practical? No, it's not practical at all. It's not something that you're going to be able to do, because you'd have to keep those superconductors at a super cold temperature, and it's going to take way more energy to do that than it would be just to use regular wires and lose a little bit of electricity along the way, or energy along the way. So a conductor then, just a reminder, is something where the electrons are not bound tightly to the nuclei, so they can be forced to move or flow when a voltage is applied to them. So when we use conductors, resistors, and insulators, what we can do with them is sort of regulate the amount of current that is flowing through a device. If we have too much current flowing through a device, or too much voltage flowing through a device, what can end up happening is we can damage the device. And so we have to control the amounts of current and the amounts of voltage in order to make sure that we don't damage the device we're using. So if, for example, you're trying to charge your cell phone and there's something that's gone haywire in your charger and it's not controlling the amount of current and voltage that's entering your phone, it could blow your phone. So that's why it's not the best idea to use a damaged charger, because what can end up happening is you're not going to get the right amounts of current or voltage flowing through. So why might it be important to know how well different materials conduct electricity? Well, because we want to regulate or have resistance to control the amount of electrons that flow and how those electrons flow. So resistors are parts of a circuit that provide high resistance and reduce the amount of current flowing through the circuit. So kind of think of it as we're putting something in its way to slow those electrons down in some way. So resistance then is the measure of how difficult it is for electrons to flow. Now, on a conductor like copper wire, resistance is low, and it's not difficult for electrons to flow through it. But we can add resistors along that copper wire that go and actually reduce the resistance, that is, or increase the resistance for those electrons, which might be advantageous. And when you guys get to doing your activity on building a circuit, I'm going to have a question that will have you thinking about why it's important to do or to build up some resistance, or else we're going to blow a particular circuit in this case. So, oh, and one last thing I didn't mention on here. Resistance is measured in ohms, and Georg Ohm was the one who came up with the idea of resistance in electrical circuits. So this actually technically, I'm going to go fix this right now. This technically should be a capital O here because it's named after somebody, but that's an entirely different lesson. And this symbol, this Greek symbol omega here, is used to represent resistance, or ohms. So that is our units, you know, M for meters, Greek symbol omega for ohms, or resistance. So devices that use resistors. The more resistance a substance has, the more the substance gains energy from each electron that passes through it. The energy gained by the substance is radiated into the surroundings, usually as either heat or light. And some examples of devices that use resistors are polygraph machines, microwave ovens, touch screens, those kinds of things. I mean, the light bulb that's shining on me right now is a resistor. It is taking the electrons that are flowing through the circuit in my light, and it's slowing them down and taking energy from them and converting it into a form of light that allows me to see what I'm doing and allows you to see me. I have a video, I think, on the next slide here that's going to have you guys have a look at polygraph machines if you want, and see what's going on with those. Solutions can also be resistors as well. A solution meaning something dissolved in water. So the more charged particles in a solution, the better it conducts water, or better it conducts. So pure water conducts a little bit of electricity, but then if you go and dissolve a bunch of salt in it to make salt water, that conducts electricity a whole lot better because the electrons are able to be bounced around between the positives and negatives in the solution there. So again, polygraph machines, just as an example, or lie detectors measure skin resistance, blood pressure, and respiration. And to measure the changes, basically they measure the changes in sweat, which is a salty solution with electrodes that are attached to the skin. And so if you want to know a little bit more about this, go ahead and go into the Google Classroom, into the resources section where the videos are, and have a click and look at that. So just to talk a little bit about switches and variable resistors, because we're going to use these, and these are employed in lots of places in your daily lives, and you may not have thought about it before. So a switch, a general plain old switch like a light switch, can create a break in the circuit that interrupts current flow. So therefore, it controls the flow of current in the circuit. It turns it on or it turns it off. So if the switch is off, the light is not on because there is a break in the circuit which controls the flow and prevents the flow from happening, or from getting to one spot to the other. When the switch is flicked, the connection is made, the circuit becomes whole again, and the light lights up. There are also things called variable resistors, okay? And variable resistors are more than just on and off. Okay, these resistors, also known as rheostats, allow you to adjust the amount of current flowing through the circuit rather than simply turning it on and off. And I think the one that works with me the best is if you've ever seen a dimmer light switch, a light switch that allows you to control how bright the light is, right? So this has got two switches on it, and this thing keeps popping up on me. There's a little switch horizontally along the bottom here that just turns the light on and off. That's a regular switch. And then that slidey thing on there that you can see, because slidey thing is a technical term, that slidey thing is meant to control, that's the rheostat, that's meant to control how much current is flowing through there. So if it's turned right down, we're only allowing a little current to flow through. If it's turned right up, we're allowing the maximum amount of current to flow through based on what that circuit can handle. Okay, I hope that makes sense. And then what ends up happening is if we, for some reason, hook up the wrong kind of device to that circuit, what can end up happening is when we turn it up to max current, what can end up happening is we end up with too much electricity flowing through that resistor, which is the light, and we can end up blowing the fuse. And the fuses, remember, we talked about in the last lesson, are used to stop the flow of current through a circuit if it's going to get to a dangerous level. Okay, and you'll have an example of some fuses in the activity that you're going to look at later on with building some circuits. So at this point, if you wanted to hit pause and take a bit of a break, you could, and look at page 303 of your textbook and answer some questions on there if you would like, questions 1 through 4 and number 6. If you wanted to hit pause and do that. And if you didn't, then please continue watching, and we will continue on to the next slide. So what I want to jump into now is I think maybe one of the trickier things to wrap your head around when it comes to this particular concept, and that is how to model or represent the electricity that's moving through a circuit. We've discussed lots of terms so far to help us describe electricity or electron flow. And the three that are the most important at this point are voltage, current, and resistance. And they're all related to one another and are often used or described by what's called a water or a hydro flow model. And these three things can be described in this hydroflow model, and it gives you an idea of how electrons move based on if it's high voltage or low voltage or high current or low current or high resistance or low resistance. There's some similarities between between flowing electricity and flowing water that are useful. First off, both flowing water and electricity come from a source. Okay, if you're talking about flowing water in the mountains, it's a glacier. That's your source. And how much water is melting that time of year, those kinds of things. In a circuit, your source could be a battery, or it could be some other source of electricity like a plug-in in the wall. Source must be constantly replenished. For water to flow, that glacier needs to be replenished. If it doesn't get replenished, the water stops flowing. For a circuit powered by a battery, that battery needs to be have enough charge left in it to continue for those electrons to flow around the circuit. And we know that both things encounter resistance, right? A river that has very few rocks in it will encounter less resistance than a river with lots of rocks in it. A circuit with very few resistors encounters less resistance. The electricity encounters less resistance than if it has lots of resistors in it. Hope that kind of makes sense to you. So if we wanted to model voltage we also called potential difference. And this term refers to the difference in electrical potential energy between 2 points in a circuit. The greater the difference, the potential difference, the greater the voltage. Okay? So similar to water pumped up a hill, a cell, battery, or generator pumps electrons to a higher voltage. So if we had just a nice lazy stream with water just flowing down that lazy stream, we would say that it has a low voltage at that point because the angle is not very steep. But if you go and you crank that angle up, the difference in pressure or the difference in height caused by cranking that stream up is going to create a great potential difference. And so if the potential difference in a battery is great, that means that we have a higher voltage. So think of it this way. Which has the higher gravitational potential energy? Water in a garden fountain or water in a water tower? Well, water in a garden fountain might only be a certain distance off the ground, and you've got your water flow coming out of that maybe only this far. If you're talking about a water tower, well, that's going to have the greatest voltage because you're bringing it from way up here to way down here. Okay? Another way I've heard to talk about this is to think about it as pressure. which is a little bit difficult to describe liquids in, but you could think of it in gases. If you have very little pressure, so not very much pushing on that water or pushing on those electrons, what's going to end up happening is you will have low voltage or low flow. Versus if you have very high voltage, you've got lots of pressure, lots of potential difference. That means that those electrons are going to have lots of stuff pushing at them to move them through whatever circuit. Okay, so we can look at this diagram as well and start to analyze it based on voltage too. You know, we can see on the left-hand side here that we've got a whole lot of water moving through, so we'd say it has a fair amount of current to it. But it doesn't look terribly tall. If we compare, the bottoms are kind of all on the same line here. This one appears taller and this one appears taller. And so these ones I'd say would have greater voltage, but definitely a lower circuit here. Lower voltage, because their potential difference between the top and the bottom is not quite so great. I would say that this one has relatively low resistance because I don't see a lot of rocks in between here. But over here, I would say this one has very low resistance compared to this one. Okay, so we can sort of play around with this. I'm not going to be able to give it any big analogies at this point, analysis of it. I just want you to get an idea. Voltage, kind of think of it as the difference between top and bottom, or how much pressure difference is there between the start and the finish. Current is how much water is moving through it at that point. And resistance is what is there to slow that water down? What is there to slow those electrons down? Okay. So if you wanted to do this, you could play around with this a little bit, and you could play around with modeling current and resistance as well, and try to imagine this based on size of pipe used to drain a reservoir or something along those lines, and fiddle around with that. And we can think of electrical resistance with wires as well. But what I did want to get into here is Ohm's law, and trying to relate those things, all of these things, voltage, current, and resistance, with something called Ohm's law. And what this is just a summary of Ohm's law. Okay, and it's giving you the three particular variables that are responsible or used in Ohm's law to do the calculations. So we have voltage, represented by the symbol V, which is measured in volts, which are also given the unit V. Current, which is represented by the symbol I, measured in amperes or amps. And resistance, represented by the symbol R, measured in ohms, using the omega symbol. And then this middle column, I'd like you guys to go back to in your notes in a second after we do the next slide, and I can sort of explain to you what's going on in here. And then if we wanted a device to measure voltage or current or resistance, we would use a voltmeter to measure voltage, an ammeter to measure current, and an ohmmeter to measure resistance. So those kind of make sense. I wanted to jump to this. This is Ohm's triangle. I'm going to give it to you. I hate triangles. And if you guys have me again in Science 10, just know that I will go away with triangles. But basically the way this works is the general formula that we often work off of is this one at the bottom here, that to calculate the voltage of something, we're going to take the current and multiply it by the resistance. Okay, so V is equal to I times R. And the way we would do that is in our triangle, we would say I'm trying to calculate V, so it's I times R. If I wanted to calculate resistance, it would be V divided by I, and if I wanted to calculate current, it would be V divided by R. So this column that we left blank in here, you can fill in these values for calculating current, resistance, and voltage. Okay, and I'll let you do that on your own. Ohm's law states that as long as temperature remains constant, the resistance of a conductor remains constant, and the current is directly proportional to the voltage applied. Now, the important term in here is that directly proportional bit. What directly proportional means is that as current increases, voltage increases, or vice versa. As voltage increases, current increases. If voltage drops, current drops. Okay, so they move together with each other. If one increases, the other increases. If one decreases, the other decreases. If one increases by half, the other increases by half. Okay, so they're moving together with each other so long as resistance remains constant. If we fiddle with resistance, then we're going to fiddle with the other two as well. All right, so this is the point where we're going to get into doing some calculations, and I'm going to get set up to show you those calculations live. And if you haven't already, you may want to grab your calculator, something to write with. I hope you've got your notes nearby you or a piece of paper to copy this down on, and then we're going to get into doing this live together in just a second. Okay, so I've got myself all set up here. So hopefully you've got all the pieces that you need, and I'm going to work through these examples together with you and show you what I'm doing. And I've got a little fancy setup here. I hope it's big enough for you to be able to see. I can't seem to make it any bigger, but hopefully you can see it, and I will write as large as I can. So these are going to be calculations that we are going to do using Ohm's law to do our calculations. So just remember, I always like to remember that V is equal to I times R. And if you wanted to set up your triangle, that's going to look like this. Okay, so we'll play around with it from there. So first example, it says a stove is connected to a 240 volt outlet. If the current flowing through the stove is 20 amps, what is the resistance of the heating element? And I've got a little sort of step-by-step guide down here in the bottom, because this is how I like to solve problems, and I'm going to teach you guys and strongly encourage you guys to get in the habit of doing this. So first thing I do is identify what's known in the question. Well, we're given 240 volts and 20 amps. Volts is a measurement of voltage, so I'm going to write that down. V is equal to 240 volts. And amps is a measurement of current. Current is I, so that's going to be 20 amps. And then the second part of the question says identify the unknown quantity. Okay? In order to do that, that is the thing that we're trying to figure out. Well, it says right here, what is the resistance? So resistance is R, and that's what we're trying to sort out. Okay, hope you're following so far. So then what I'm going to have to do is I'm going to go back up to here, and I'm going to say, okay, resistance is what I'm trying to figure out. Put my finger over that to remember that that's what I'm trying to figure out. And we're going to take voltage and divide it by current. So I'm going to write that here. Resistance, so this is using the correct formula, is voltage divided by current, okay? And then I'm going to substitute my numbers in. V, so this goes in here. So that becomes 240 volts divided by, and then I is this, so it's going to be 20 amps. Then if you need to, you can take your calculator out, okay, turn it on, right? And then all I'm going to do, remember, this over that means division. So 240 divided by 20 is going to give me the answer of 12 and then ohms. Okay, remember ohms, and that's my horribly drawn Greek symbol omega. And that is how you answer your first example question. So I hope that makes sense to you. And what I'm going to do is take that and throw it away. And we'll do example number 2. We're going to follow the same procedure as we did down here. So I'll read the question. As a microwave is connected to a 60 volt outlet, if the current flowing through the microwave is 9 amps, what is the resistance? So this is the same style of question that we did in the last one. Okay, so voltage is 60 volts, current is 9.0 amps, resistance is what we're trying to figure out. We'll go back to our triangle, which was V, I, and R. Sorry I drew that so small. Okay, we are trying to figure out resistance again, so it's going to be V over I again. So resistance is V over I. V goes there, I goes there. So it's 60 volts over 9.0 amps. We're going to take our calculator out again, okay, plunk it up on here so you guys can see it, and we'll just do 60 divided by 9, and our answer is 6.6 repeating. I would say let's round that to the nearest tenth, just to be happy. Usually a PAT question or something would tell you round to the nearest tenth or something along those lines. So we'll round it to the nearest tenth, which is going to be 6.7 ohms. Okay. Oh, the other thing I didn't do on the last one, I like to put a box around my final answer, because that way I know as the teacher that that's what you're telling me your final answer is. Okay, so I hope that makes sense. Pause right now if you need to. I am going to do the next example. Okay, throw that other one away. So we're going to follow the same procedure again. Read through the question carefully. A 12-volt battery, well, there's a measurement, runs through a 15 ohm resistor. What current is produced? Okay, so we've got all the stuff we need to know. This is our volts, or voltage, 12 volts. Okay, here 15 ohms. Ohms is the measurement of resistance, so it's going to be 15 ohms. Okay. And then lastly, we're asked to figure out what is the current. I, question mark. We'll go back to our little triangle we've been fiddling with. Okay, so we've got V, I, and R. Okay, so this case now we're trying to figure out I. So that is going to be V divided by R. So I is V over R. V goes here. R goes here. So it's going to be, oh, this is the way I did it last time, 12.0 volts over 15.0 ohms. And then that is going to give us our answer for current. So it'll be, see that, 12 divided by 15 gives us an answer of 0.8. And our units of measurement for current are, that's right, amps. Okay, so 0.8 amps, put a box around it because that's the way we like to do it. So I hope that makes sense to you. I am going to pause for just a second to get that unset up and then jump back in, but you won't even know I paused at all. Okay, so I am back. Oops, I forgot to move my video. Just give me a second here. I'm going to put it down on the bottom right. I am back. I hope I didn't go too quickly through those examples, but the advantage of having a video means that you can always go back and have a look at them again. I did not do example number 4 with you, and I'm going to leave you to try that one on your own, but I will tell you right now that the answer is 1,517 volts. So try that on your own right now if you'd like, and see if you can get the correct answer. And I am going to move on. So there are test meters, things that we can use to measure the voltage between two objects. Okay, one of it is called a voltmeter, and voltage we know is the potential difference between 2 points, and it's measured by a voltmeter. And so the 2 points, the potential difference we're measuring is between here, and between here and here. And this is, by the way, a schematic diagram of a circuit. And what you can see, this represents a 1.5 volt battery, and this represents 3 1.5 volt batteries, which total 4.5 volts. Okay, the voltage drop across a resistor or other device in a circuit is what a voltage drop is, and meters are used to measure small amounts of voltages as well, and we would call those meters micro or millivolt meters that are measuring the tiny amounts of drops in voltage. We don't tend to use those around our houses too terribly often. Ammeters are used to measure electric current or rate of flow of electricity. Remember, the way I remember it, voltmeter measures voltage, that makes sense. Ammeter measures amperes, right? That makes sense. And ammeters measure how many electrons move past a point in a circuit each second. The more electrons moving by per second, the greater the flow, so the greater the current. If a circuit consists of a continuous loop, you can insert the ammeter between any two circuit components, and it's going to give you the same reading anywhere on there. A galvanometer is a device used for detecting and measuring very tiny amounts of current, and that is something that that we don't tend to use terribly often. But remember, tiny amounts of current are good, and that's what a lot of our devices use to keep them safe for us. A multimeter is a device that can measure voltage, current, or resistance on a circuit, and one of the videos that I have in there somewhere uses a multimeter that you guys can have a look at, I believe it is the one on what is an ampere that shows a multimeter in use. So it'd be worthwhile having a look at that video. At this point, I should mention those videos too. I've got 3 videos up there, one on Ohm's law, one on amperes, and one on voltage that I think are a really good thing for you guys to look at. If you want to pause now and do some practice, you can. I'm going to move on to talking about analyzing and building circuits. So when we build a circuit which allows us to take advantage of electricity to make it do some work for us, these circuits can be drawn out and represented in diagrams. And we saw a couple of examples of them back here at the bottom. The bottom here is a circuit diagram. We saw a circuit diagram in here. And you guys are going to be drawing some in the activity that I set out for you. Circuit diagrams or schematics use special symbols that show the components and connection of components before the diagram is built. The schematic diagrams make it easier to plan and analyze circuits. And you can even build circuits using technology, using a computer, and run it through as a model or a trial thing on a computer and see if it's even going to work before you try it out in real life, which I think is kind of cool. And that certainly wasn't available for people 50 or 100 years ago. Circuits, remember, require 4 components. We talked about this in concept D1. They need an electrical source that supplies energy or electrons to it. They need wires or a conductor to provide a pathway for the electrons or current to flow through. They need a load that converts electrical energy into some other type, so a light, for example. And they can have switches that turn on or off or direct current along different paths in that particular circuit. There are some basic electrical symbols that I want you guys to become comfortable with for these, and your activity that you're going to do on circuit building will have you becoming comfortable with some of these electrical symbols. So a single straight line on a schematic circuit diagram represents a conducting something connecting, a wire, something along those lines. A squiggly line or a box like this represents a resistor. A circle with an A is an ammeter. A circle with a V is a voltmeter. A battery is a short line, a long line and a short line. A lamp or a globe is a circle with something inside it. I often put it as a little squiggly inside there to represent a lamp. A circle with an M is a motor. One of these things with a here's your wire, and then it comes up and makes a break and then goes over here. That's a switch. As soon as that comes down, the switch is on. And then there's a bunch of other sort of examples down here for you. The ones I really want you to become comfortable with: wire, lamp, there's that little squiggly I was talking about, fuses, resistors, don't worry about these guys, connected conductors or wires, don't worry about the ground. Cell is one individual cell, and then a whole bunch of them together are a battery. You know, voltmeters, you know, switches. Those are the ones I think are most important. I'm going to wrap up this with talking about parallel and series circuits. Okay, there's 2 kinds of circuits that we deal with, parallel and series, and each is defined by the number of branches that are present in the circuit, and each has its own advantages and disadvantages. A series circuit is one in which there is only one pathway for the current. And if that pathway is interrupted, the whole circuit cannot function. Okay? And so A series circuit, and I don't have the ability to draw on this program. Give me just a second. I'll see if I can sort that out. So I'm going to pop back in and just show you a couple of images here. So remember, we're talking about series circuits, and so this is a diagram that I would show you of a series circuit. And a series circuit means that whatever resistors you have are hooked up in order along the same line. And so that means there's a resistor here, here, and here, and electricity is flowing from this way around, and the electricity passes through each one of these in sequence. And if I made a cut, let's say down here, what would happen is the electricity for the whole system would shut down and all of these would go out. Okay, so just jumping back into right here, the advantages and disadvantages of series circuits. Adding components increases the total resistance and thus reduces the amount of the current in the circuit. So for example, adding bulbs to a string of Christmas lights makes each light get a little bit dimmer, which might be an advantage if you're trying to control the amount of light coming out of something, but a disadvantage because you're running out of brightness on your string of light bulbs. One faulty component can also interrupt the current flow. So if a light bulb goes out, if one of those resistors was a light bulb and it burns out, your circuit is broken and nothing is going to continue. And if you've got 50 light bulbs on a string of lights, then it's not going to work so well. Switches are often wired in a series that can turn off all the electricity in a circuit for convenience or for safety. So your circuits in your house are often wired in series in order to make sure that we can shut off the entire circuit all at once if we need to, out of safety reasons. Okay, so that's series circuits. You've got each of the components all on the same line, basically. In your circuit. There's also parallel circuits, and they contain a separate current pathway for each section or component of the circuit. And an interruption or break in one pathway does not affect others. So I'll show you what that looks like here. Here's a parallel circuit. So instead of them being lined up along the outside here, we have one pathway, two pathways, three pathways for the current to travel. And so what would happen is if there's a disruption here, this resistor will not work anymore. If this is a light, it will go out. But these two will keep running. If there's an interruption here or here, these two will keep running, and so on. So the advantage of what's going on here is that we can have, let's say, a light bulb burn out, and the other two will stay going. Or this to be turned off, and these two will stay going. So this might, if you think of this as the light in your bedroom, your kitchen, and your dining room, what might end up happening is you could have this turned off and this turned off, but this could still be on. If it was in a series circuit, then you would have a switch here and all three would go off. I hope that kind of makes sense to you. So jumping back into the presentation here, we'll just talk about advantages and disadvantages of parallel circuits. Adding a new pathway with more resistors does not affect the resistance in other pathways, meaning that lights aren't going to get dimmer, which is nice. Adding resistors in parallel actually decreases the total resistance of the circuit. It's like drinking through two straws instead of one. It allows you to take out the same amount but with less resistance. The voltage change in the branch is equal as well, which means that you're getting the same voltage always all the way through in each of those parallel circuits, but it requires more switches or safety features. So that might be a disadvantage. It's a little more expensive and time consuming to put a parallel circuit together, but ultimately it has a lot of advantages to it. Parallel circuits are more commonly used in households and devices than series circuits. Imagine what would happen if your house used series circuits instead of a number of parallel circuits. If you only had one series circuit that ran your upstairs and you had a whole bunch of stuff on at once, all your lights would be super dim. The other thing that would happen is if one of those devices stopped working, everything else would go off. And so we've learned that parallel circuits are likely the best ones for us to use because it allows a heck of a lot more control. It allows things to stay bright or operating at the same voltages and currents on each of their little separate pathways. Just a quick talk about microcircuits, and then we're done. I'm sorry, this was a long concept for us to go through, but there's a lot in here and a lot to explain. Microcircuits are tiny circuits that we find in a lot of our consumer electronics, like our cell phones and things like that. And they use transistors instead of switches to control the amount of current moving through an area. And the transistors are usually made of 3 layers of silicon that are sandwiched together. This is just giving you an idea of some of the micro circuits that we've got going on. There's one there, and this is an ant actually holding onto a printed microcircuit. These transistors have no moving parts and operate on digital code running through the middle layer of the transistor to control the movement of current through each circuit. The latest microcircuits have more than 1 million components in a square centimeter, so you can think those are tiny circuits. Okay. That's it. I'm done talking for this concept, very long concept. If you made it this far, high five to you. That was a slog. There are a few more questions you can do out of your textbook if you'd like to. What I didn't include on here is the activity on circuit building that I would like you to do. And you can find that in the Google Classroom under Unit D. It'll be called Activity Circuit Building. Do it, please. I think it's going to put a bunch of pieces together for you when it comes to circuits, when it comes to voltage, resistance, and current. And it'll be kind of fun because you get to mess around with this app, this website that allows you to build stuff. And some of you I know would like to build stuff and then blow it up. Well, you can do it virtually this way, which is kind of fun. If you've got time, jump on and do worksheet number 2 for concept D2. That'll reinforce some of the things that I think are important. And then as always, there will be a practice quiz waiting for you as well. Do the practice quiz first, wait for my feedback, and then jump into the summative quiz once I've said you're okay to do so. All right, thanks everyone. That was a slog. I appreciate you all sticking through and making it this far. I'm looking at the timer and I've recorded 47 minutes of video here, so well done getting through that. Please make sure you get a hold of me if you have any questions, email, drop me a line on the Google Classroom. I'd love to hear from you just to make sure you're doing okay, or if there's anything else I can do for you. As always, stay healthy, and hey, I'll see you guys, and we'll talk in Concept D3.